Okay, so we're recording. Okay, a little bit of a late start, and I'm still waiting for 40% of the class. So I'm going to pass the time with a mathematical horse joke. Okay. Theorem. All horses have an infinite number of legs. First, the two lemmas. Number one, all horses are the same color.
Okay.
Proof by induction. Obviously, one horse is the same color, so it's true for n equal 1. Now we assume that we have k horses that are the same color, and now consider k plus 1. Well, if you remove one horse from a k plus 1, you have a set of k horses. By induction, they must be the same color. And since the horse that was removed is arbitrary, then all k plus 1 horses are the same color. So all horses are the same color. Lemma 2. If a number is both even and odd, then it must be infinite. Well, if we have a number that is both even and odd and finite, then n is equal to 2a for some integer a, and as because it's even, and n is equal to 2a plus 1 because it's odd. Well, from that, you said 2a equals 2a plus 1, you get 0 equals 1. It's a contradiction. Therefore, the number cannot be finite. So, all right. Now, the theorem itself. All horses have 4 legs in front and 2 legs in back. F-O-R-E, 4 legs. As a horse owner would know. Now, 6 is an even number, but 6 is clearly an odd number of legs for a horse to have. So the number of legs in a horse is both even and odd, and therefore must be infinite. And you say, well, my horse has 4 legs. That is a horse of a different color, which contradicts the first lemma. So there you go.
This is a black horse.
Yeah.
Her name is Harley. I did not name her, but she is named after the motorcycle company.
Oh, okay.
It's a cute story if you want to kill more time. It really is a cute story.
I was hoping it would be Harley Quinn.
No, she was definitely named after the motorcycle company, which is why I said I did not name her. I got her as a 4-year-old with the name already. And she's 20. I've had her for 16 years.
All right.
I need to live another 10 more years. I told her, like, Harley, please, I beg you, just live through my PhD program. Please
10 years? You're going to spend 10 years getting your PhD?
I mean, I would love her to just live for 10 more years, so I'd put her at 30 and I could have 10 more years with her.
Okay.
But I was like, at the minimum, I need you to just live through my PhD program, Harley, please, for the love of God.
Okay. Which hopefully would not take anywhere near.
I'm hoping to be done in like 3 or 4.
Okay, yeah, that's doable, and it has been done. Well, if you look at when I officially started at Stanford to the time that my PhD was conferred, that total time span is 12 years. But I was actually on leave for 6 of them and working full time. And also, it also includes time getting a master's. But yeah, so if I want any of you to get done faster than that. Well, yeah, I've had students that have gone for fast and slow, but it all depends on each person's circumstances. So.
I just need all my everyone to be healthy because them all getting sick at the same time is not helpful.
Yeah.
There's 3 of them and they're all having issues right now. There's Samson.
Oh, okay.
Now we can start.
Okay.
Now we're really going to keep putting into the class. We have 2 of them tomorrow. I have 2 tomorrow. The last 2, I was able to block out so I can go help with testing and vaccine. And they're doing the 2 classes at the same time testing, which is nice.
Okay, and Chandler is coming. Let's see. Dang it. It's a bit autocorrect. All right, now, finally, actually dealing with numerical methods starting today, and finite difference. Okay, so. Oh, okay, looks like she is close. All right. Board is really yicky. Like, all these location marks. Let's make it a little better. And yes, I'm also slightly stalling so that everybody can be here.
I was just gonna say, you could just blame it on the weather, because it's really humid and it's unpleasant.
I don't have to go to my car.
Okay.
I think I'll do
So-
that.
Okay. So. So first I'll talk about what is a finite difference stencil and like what is it used for and how can we obtain them. So the goal is to find coefficients that I'll label let's see.
And that says stencils at the end of the general approach, correct? Okay.
Yeah,
Just wanted to make sure.
Yeah, so that's what this section is about. Okay. E0, A1, up to AM. So that the derivative of a function, or today the J derivative. Okay. So, as you can tell, you've missed practically nothing. Okay. All right. Well, actually, what have you guys missed? The horse-themed math joke.
Wait, what?
I told a mathematical joke about horses. Yeah. So, but it is recorded. So. Yeah, that's what. Well, I was inspired to that by Rachel talking about the difficulties with her own horses. So.
I highly recommend you avoid them as a pet.
Yeah. So, so you can go to the video, the beginning, and catch it there. Okay. So the idea is we want to approximate the J derivative of some function u at a certain point x naught by okay, using a linear combination of values of u at selected points. So we only want a derivative at this one point x naught, and we use the value of u at x naught and surrounding points to approximate the derivative. And there is going to be some error, of course, in doing that. We want to try to make that error as small as possible. Okay. So how do we do that? Okay. We would use Taylor expansion. So u of xi is equal to infinite sum. Okay. I should use a different letter here. Okay. Yeah, I'll fix that in the notes too. All right. So that is the kth derivative at x naught over k factorial times xi bar to the kth power, where xi bar is a shorthand for xi minus x naught. So this is what you really have in here for Taylor's theorem. Because this Taylor expansion is centered at x naught. So what you can do is substitute this Taylor expansion into here. So now we have this one derivative that we're looking for at x naught, expressed in terms of this sum that involves our unknown coefficients and these spacings in points, and also all the derivatives of u, but only at x naught. All right. Now, so when I make a substitution, then we have okay, so we're going to have a double summation on one side. So oh, and keep in mind, this notation, I know you've seen it before in other classes, where I have a superscript in parentheses that refers to derivatives. So this is the kth derivative of u at x naught. Okay, times ai. That is equal to okay. All right. Now, let's see. Now, so what I'm going to do now is rearrange this. By putting this some on the outside. And I'll put the kth derivative at x naught outside of parentheses. Everything else goes inside. So now what I have here is, let's see. Actually, I'm going to put the k factorial out here too. So everything is inside depends on I. Okay. Is equal to a j derivative. So I'm just using the same notation on both sides, but here with j and here with k. All right. So now the way to look at it is, I have a linear combination of all the derivatives of u at x naught, but I want that linear combination to be equal to just a specific derivative at x naught. So the only way I can achieve this is I want what's in these parentheses to be equal to 0
I never said it was pleasant, but you would have one video file to upload.
True. Well, maybe not in today's post-processing, but I might come back to it later. Okay, so what shit show this class is. Okay, take two. So this is a system of equations that we solved for coefficients a0 to am. Now, the thing is, I've chosen n+1 coefficients. Well, that number of coefficients chosen in advance. You prescribe up front. How many points do you want to use to approximate whatever derivative you want? But because we've chosen n+1 coefficients, we can only have m+1 of these equations satisfied out of the infinity that we actually have. Because by the rules of linear algebra, like to have a solution exist at all, let alone be unique. Otherwise, we have an overdetermined system that may not have a solution. So we obviously have to include, since I have infinitely many k to work with, well, I obviously have to include k equals j, because that's the derivative I want. But it's best to include k starting from 0 up to m, because as you choose points xi that are close to x naught, and you raise them to the kth power, those differences will get smaller and smaller. So whatever terms you're leaving out will be the smallest ones if they correspond to the higher values of k. So that's why, so I and k equals 0, 1, 2, up to m, to minimize the error. So that the left out terms will be smaller. Okay. All right, so questions about this system and how it came about before I do some examples. Okay. Oh, what I was asking when things went down. When you have a matrix like this, where we have a predefined set of x values, these xi, And in the matrix, they're raised to different powers. So in this case, each row consists of these x values raised to the kth power. That kind of matrix has a name. Does that ring a bell for anyone? Yeah, it's a van der Waals matrix. Okay, so that's often used when approximating something effectively by a polynomial. Because really what we're doing is we're replacing u by its Taylor polynomial up to degree m, and taking and matching its derivative. So that's how a lot of things work with approximating derivatives and integrals. Whatever you want to approximate the derivative or integral of, you approximate that function by a polynomial, and then you compute the derivative or integral of a polynomial exactly. Just because that's the easiest one to do. Okay. So now we'll take a look at what happens when we use this system. So I'm going to record the last 20 minutes just to have something. Oh, I hate technology. Okay. So we'll do one involving second derivative. Yeah, so there may not have been a problem with Microsoft at all, just EduRoam.
Technology is great until it doesn't want to work.
Okay. Well, I mean, what we're doing is in the hands of iTech, and that says it all. Okay, so now another example, j equals 2 for second derivative. M must be at least equal to j, so that'll also be 2, so 3 points. So u double prime at x naught will be approximated by a0 u of x naught plus a1 u of x1 plus a2 u of x2. Whereas before, x1 is x naught plus h, x2 is x naught minus h. So I'll have the same x bars. So now for our system of equations, the matrix will be exactly the same as with the 3-point approximation of the first derivative. It's just the right-hand side has changed because we're approximating a different derivative now. 0, 0, 2. Because it's whatever derivative you want, second derivative, that factorial is what goes in the j plus first spot. So now what you get is a0 is minus 2 over h squared. A1 is and a2 are both equal to 1 over h squared. So once again, they all sum to 0. So that's true no matter what order derivative you're approximating. So u double prime at x naught is equal to u of x1, u of x naught minus h, minus 2 u of x naught, plus u of x naught plus h all over h squared plus big O of h squared error. Now what's interesting here is we covered the first three terms of a Taylor series that have terms of order 1 or h squared. The first the first terms in the Taylor series that are not matched have order h cubed. So you might think, oh, well, if those first unmatched terms are of order h cubed, so then we have to divide by h squared, the error should be order h. But we have symmetry in this case. And that's why the error is order h squared. Because normally, if you're trying to approximate a jth derivative, and you use j plus 1 points, which is the bare minimum to get an approximation at all, you think your error would be order h. And in the general case, that's true. But sometimes symmetry can give you a little extra degree of accuracy. All right, now everything I've shown you is in one space dimension using a one-dimensional Taylor expansion. But you can also do a multi-dimensional Taylor expansion to approximate derivatives in higher space dimensions. So I'll just give an example, like a final result. So in 2D, the Laplacian. Okay. So the Laplacian of u at a point x naught, y naught is equal to actually, it's going to be what you get from using two of these. One for second derivative with respect to x, the other for second derivative with respect to y. So the coefficients you'll actually see up here. So for this is for second derivative with respect to x. This is plus. This is second derivative with respect to y. And then minus 4 u of x naught, y naught. Why is it 4? Because you have two of these terms, one for uxx, the other for uyy. They combine. And then you have u of x naught minus h, y naught, and u of x naught, y naught, minus h. So in this case, we're assuming equal spacing in x and y, which is not always the case, but it's convenient here, and divided by x squared. And the error is order h squared again. Okay. So by using this approximation for uxx, same approximation for uyy, adding them together, you get that. But you can also arrive at it by in a more direct way by doing a two-dimensional Taylor expansion of u centered at x naught, y naught. Okay.
I have a question.
Yep.
So you have notation for J and M. It appears as though J is always less than or equal to M.
I'm sorry.
Like J is always less than or equal to M. Is that how this is?
Yeah, it has to be. Because otherwise, your system of equations won't have something to have an equation that involves matching the actual derivative you want. So in general, so in most cases, let's see. Okay, so first derivative, I gave a general order of accuracy statement that it was order h to the m. But more broadly, takes both J and M into account. So the order of accuracy would be H to the okay. Yeah, so that's how it would work out generally. However, can be higher due to symmetry. So the second example I gave, first derivative, j equals 1, but using 3 points, so m equals 2, that led to order h squared accuracy. But this example here, j and n were both 2, so normally 3 points per second derivative is order h to the first accuracy, but by the symmetry, the leading error term turned out to be 0, so that's why it's order h squared. But this is why we need m to be greater than or equal to j, because otherwise your error will not go to 0 as h goes to 0. That's the key. So you would never be able to get a good approximation of, say, the fourth derivative if you're only going to use 3 points, for example. Okay. I'm looking at what else I have here. Okay, I think what I could do is adjust what I'm covering, since there isn't much time left today, and that the next thing coming up will take longer than 10 minutes, and I don't want to fragment it. But are there any questions about this? You've all been able to start the first homework problem by now. Any questions on that?
Yeah.
Okay.
So, like, I looked at the hints, and so just in the notes you had the derivative. We had first derivative of t.
Yeah.
So for the assignment we had two derivatives, the second derivative utt.
Yeah.
So that gives second order ODE.
Yes.
Which we solved using finding the roots.
Yep.
Right. So when I found the roots, I got negative d plus or minus square root of d squared minus k squared.
Yeah.
So, and you said that becomes the solution multiplied by exponential ikx, right?
Yeah.
So, but where I got confused, where it felt like there was nothing really in homework 1. That's how I felt, because once I did that and get that solution, we said to check for the other. I forgot what you said we should check, but we need to factor out ik.
Yeah.
And so when you factor ik, I don't really see what we do with it, like, because we had ikx on both terms. So when we factor out ik, we're left with d. I can't remember the factorization, but like I didn't know what to do with that. It said if the ik term disappears from the r of k to the 10.
Yeah.
If it doesn't disappear, then it means I can't remember.
Okay. Okay. So one thing is to keep in mind, since depending on the values of d and k, the roots may or may not be complex.
Yeah,
so,
because that was where I got confused. Like, because when we did PD 606, when we came across such solution, we considered 3 cases.
Yeah.
When D is greater than K, when D equals K, and then when D is less than K. But we're not doing that here.
Well, yes, you can. So you do need to examine the possible scenarios.
So, like, there was no information to do that, because that's another thing I didn't get. It says periodic boundary conditions.
Yeah.
Right?
Well, that's what justifies using e to the ikx in the first place.
Yeah, so but that does not help us when we want to find, when we want to consider the three cases. So when we consider the three cases, we need the initial condition.
No, I'm saying like, okay. What I mean is you're considering cases of, but really it's okay, maybe we're talking about different sets of cases here. What I really mean is the discriminant.
Yeah.
Okay, because that, so you don't need to think in terms of initial data for that, because the relationship between D and K, the discriminant lets you know, okay, for this root that you have from a quadratic formula, what from that is the real part, and what from there is the imaginary part, if there is an imaginary part, because okay, so when you have your e to the I k x minus something, the only part of the root that should go in here is the imaginary part, because the real part that should be considered separately, so you can tell, okay, based on whether the real part is positive, negative, or zero, but we're going to have exponential growth or decay or remaining stationary. So as far as determining, like, if there's any sort of advection or dispersion, you're focusing on the imaginary part, if there is one, and that's what you factor the IK out of.
So like when we go to the cases, right?
Yeah.
So like case one I did was B equals K. So the discriminant becomes 0.
Yeah.
I'm getting a real part.
Right.
What do we do with that solution?
So in that case, all right. So that's okay. So when your root is entirely real, then it's a matter of, okay, then that's either a case of diffusion for negative real part, or exponential growth if it's positive. So that's really the only statement you can make in that case. Okay, I'm pulling up a problem here. Okay. Yeah. So since the question says, show waves e to the ikx travel frequency dependent velocities. Okay. And because what's happening is when you do have an imaginary part, and after you factor out IK, your speed is whatever's multiplying t. So you're getting a hold of what that expression is. So in that case, all you're showing is that, okay, that happens to depend on k.
That's when we have an imaginary part.
Yes. Yes. So
I feel like, right, from what you've explained, I feel like I get an imaginary part.
Okay.
Or like two of the cases we're considering.
Yeah.
Will give us the real solution.
Okay.
Because when the discriminant is 0, we get just one real solution.
Yeah. Oh, okay. Here's the thing, though. Only D is a constant value. K goes from plus or minus infinity. So what that means is for your solution, because your solution is a collection of infinitely many waves for all the K. So for certain K, you might only have a real root. And so those particular waves would like only be diffusing. But the rest of the waves that'll produce an imaginary part will travel with a frequency-dependent speed. So it's because k is allowed to vary over a whole real line that all the situations are going to come up. So yeah, you may not have all waves traveling depending on the value of d, but some will.
Yes, well, in this case now, we're not giving a value for t.
Right, yeah, but it's not necessary because the condition is for k such that you get a negative discriminant. So that's how you're going to describe it. So for verbose k, you have a traveling wave. Here's the speed. It depends on k. So your answer will include a relationship, like a condition on relationship between d and k that indicates which waves will do that.
We'll also consider.
Okay, yeah, but the point is, like, yeah, so if I had given you a specific value of d, then okay, then you could pinpoint numerically which waves, which frequencies k are behaving that way. But instead, it's just a symbolic relationship. But you're still able to determine, at least in terms of the unknown value of d, which waves behave that way. And then from the factoring, you can see, okay, here's the speed for the waves for which that applies. And you'll see from there the k dependence.
Okay.
All right. Oh, and now we're out of time. That went well. Okay, so I'll upload something. And let's hope it's not a shit show on Thursday.